Chapter 26, Capacitance and Dielectrics. We have so far studied how to calculate the electric field and electric potential produced by charges. It is now time for us to start discussing devices, electrical devices that we can put in the electrical circuit. Oftentimes we need to store some charge as part of the electrical circuit. And when it comes to storing charge on a conductor, a common concept we have to deal with is so-called capacitance. So what is capacitance? Well, capacitance, this word comes from the word capacity. For example, if you have two containers, both of which you can store some water into it. You know, for each of them, as I pour more water into them, the water level will rise, right? But due to the different shape of these two containers, even if they have the same water level, you know, the height here and the height there are the same, you know, they're not going to necessarily contain the same amount of water. Obviously, in this case, you can contain more water, even though the water level still is the same as that of the other container. So this is an example in which we have to deal with the relationship between the amount of water and the corresponding height of the water level reached. In the case of electric field, if I put some charge on a piece of conductor, some positive charge, say, then you know necessarily the electrical potential will rise, right? And if you double the amount of charge that you put onto this metal piece, then the electric field everywhere in the space will be doubled, and therefore the electric potential of this metal piece will also be doubled. That tells us that if you look at the charge Q on the capacitor on this metal piece, and then you look at the potential V it is produced, Q and V are proportional to each other, because when you double Q, you also double V, right? And therefore the ratio of Q over V would stay the same, right? And this is an important concept for us to realize, because even though for different objects, for different metal pieces, this ratio Q over V may not be the same, but for the same metal piece, okay, the ratio of Q over V will stay the same, and this ratio is called electrical capacitance. And this object, this metal piece which can store charge, is called a capacitor. Okay, so what's a capacitor? It is something that can store electric charge, and it's got a certain amount of capacitance, which is based on this formula of Q over V. It's very much like volume of the water versus the height of the water level. You can think of the volume of water as the charge stored on this capacitor, and you can think of the height of water level as the corresponding voltage or potential that is created by the presence of such a charge, such that Q over V remains the same for the same piece of metal. Okay, let's be more elaborate on the definition of capacitance. It turns out there are two definitions. The first one is an uncommon definition. It involves a single piece of conductor, say, you know, a piece of metal. Okay, nothing else, just a single piece. And we put some charge on it. The charge is Q. As a result, there is a potential produced on this piece of metal. By definition, I'm setting V equal to 0 at infinity far away. Okay, so imagine there's an isolated piece of conductor. I put some charge on it, and using V equal to 0 at infinity, there is a certain amount of potential produced or set up on this piece of metal. And then the way we define the capacitance of such a single piece of metal is just as before on the previous page, Q over V. Q over V. This is how we define it. Okay, how is this capacitance determined? Well, let's look at a very simple example. We use a very simple geometry, which is a sphere, okay? And the Earth would be an example. Suppose I have a spherical conductor, right? A spherical conductor of radius r. That's the only geometrical dimension we have to deal with here. And it's a radially symmetrical electric field, so that it is quite simple to calculate V. Okay, it's quite simple to calculate V. Suppose I put some charge Q on it, right? Put charge Q on it, and you will have a spherically symmetrical electric field, right? So if V is 0 at infinity, what is the value of V on this capacitor or on this metallic sphere? Well, we know how to calculate that, because all the way from infinity to the surface, the electric field is equivalent to that of a single point charge located at the center of the sphere, and that is just kq over r squared. Integrating all the way from here to there, one can easily calculate the electric field on the surface of this conductor, and we learned how to do that in the previous chapter. And I'm just going to copy the answer here. Very simple. V equals k q over r. Right? You recall that example? Okay. Now k itself is 1 over 4 pi epsilon naught. So I'm going to rewrite this as q over 4 pi epsilon naught r. K is a very large number, about 9 billion. Therefore, epsilon naught is an extremely small number as a result. Now, you notice that indeed V and Q are proportional to each other. So therefore, the ratio in this case, C, would be Q over V, which is Q divided by this guy. Okay, so it's Q divided by Q over 4 pi epsilon naught R. And that equals to 4 pi epsilon naught times R. That is the value of the capacitance of an isolated spherical conductor. Okay, indeed, it has nothing to do with Q. The ratio is independent of Q. It does depend on the geometry, however. In our case, again, since it's a sphere, the only geometrical parameter is the radius. The radius right here. So you see, it is proportional to the radius. The bigger the sphere, the greater its capacitance. Does that make sense? Well, think about it. It does, okay? Because it's Q over V, right? Suppose I want a greater capacitance. Then I want to put a certain amount of charge, and I want the corresponding voltage to be small, right? I want a corresponding potential raised on this conductor to be small. And if all these charges are heavily concentrated on a smaller sphere and they're very close to each other, producing a very strong electric field nearby, therefore that would make V greater, right? And if you disperse these charges over a much greater sphere, then these charges are pretty far away from each other. The electric field is weaker, and therefore V will be smaller. So C will be greater. So a greater sphere gets you a greater electrical capacitance. But let's not forget that epsilon naught is an extremely small value. In fact, you look at 4 pi epsilon naught here. That in fact is 1 over k. And how much is k equal to? K is 8.99 times 10 to the 9. It is about 9 billion. Okay, so this part, 4 pi epsilon naught, is 1 over 9 billion, roughly, in SI system. So even if you have a very large radius, you will still end up with a relatively small value of C. As a matter of fact, the SI unit for C, the capacitance, as you know, is that of charge divided by that of the potential, and that will be, of course, Coulomb over volt. And we have a name for it, okay? Just, the same convention we've been using all along. We name it after a physicist. The physicist in this particular case is Michael Faraday, and then we call it 1F, F standing for farad, which is the short for Faraday. Okay, so 1 farad is defined as 1 Coulomb over 1 volt. And if you use farad as the prime SI unit for capacitance, then you will find that farad is, generally speaking, an extremely large unit. Okay, it's easy to get 1 volt, right? Or even 100 volts. It's not that hard. But it is extremely difficult to get a 1 farad capacitor. Think about it. The radius r. The bigger r is, the greater the capacitance. What is the biggest sphere we can find? Well, how about the Earth itself? The Earth actually is a weak conductor. Let's say it's, let's idealize it. Let's say it's an ideal conductor. So we look at an ideal conductor as big as the Earth itself. Okay, now that is as big as we can find, right? You put an R there. How much is the C value you're going to get? Are we going to get 1 farad? A million farad? Well, let's see here. 4 pi epsilon naught. That is roughly 1 over 9 billion. Okay, 9 times 10 to the 9 in SI system. And R, what is the radius of the Earth? Do you recall? It's about 4,000 miles, or 6,400 kilometers, or 6.4 times 10 to the 6 meters. That's the prime SI unit. So you take this divided by that, you will get the value of C of the Earth in farad. And you can see here, this is a lot less than 1. Right? It's a lot less than 1. In fact, it's about 70 millifarad, not million, okay, milli. It was about 0.000, how many zeros? 0.007. Okay, that's all there is to it. It's a lot less than 1 farad, even for something as big as the Earth. Okay, so that's one thing I want you to pay attention to. Farad is a very big unit. You give me a 1 volt potential difference, I will believe you. But you tell me that you hold in your hand a 1 farad capacitor, guess what? I will not believe you. Okay, it's too big. But of course, later on in this chapter, we are going to study the concept of so-called dielectrics. That's in the title of the textbook. And the reason why we want to study dielectrics is because we want to find a way to increase the capacitance. Okay, so that will come up later. Now, the second definition is the common definition of capacitance. And in this case, we have more than 1 piece. Okay, that in fact is the working definition of a capacitor in a real electronic circuit. We have 2 metal pieces, 2 conductors. Okay, they are not connected by a wire, so that they do not have the same potential, otherwise there's no point. This piece carries a charge positive Q, and that piece carries a charge negative Q, equal in magnitude and opposite in sign. As a result, you see electric fields, right? Field lines going from positive to negative, and there is therefore a potential difference between them. Okay, a potential difference between them, and let's call that potential difference V. Okay, so this V is not the same as the previous V. The previous V is, based on V equal to 0 setting and infinity. Here, this V is really just delta V. Okay, the potential difference between these two, and then we define C as Q over delta V. Delta V is often just called V, okay? So symbolically, as the same as the text, we just call it V. V really is just the potential difference between these two. It's just delta V. Okay, now this definition is not quite the same as the one before, but this is the one we're going to use from now on. It is clear that when you double this Q and double that negative Q, then the electric field everywhere will be doubled. Okay? The electric field everywhere will be doubled, and so will be delta V. And therefore, again, Q over delta V would remain the same. So it does not depend on Q, but what does it depend on? Well, once again, just like we saw in the case of a spherical capacitor, it will depend on the geometry, okay? How big this piece is and that piece is, that sort of thing. So that is the common or working definition of a real capacitor, and that's how we calculate its capacitance. So with this new definition, we can now start with some examples how to calculate C. All we have to do is this, assuming that there is a charge Q here and a charge negative Q there. As a result, let us find the electric field between here and there, everywhere, and let us integrate this electric field over this distance from here to there. That will give us delta V, or V. And from that, we can find the ratio of Q over V. And that, by definition, is the capacitance.